All right. Yes. Is this audible to all of you?
Yes, ma'am.
Assalamualaikum, teacher.
Walaikum assalam. All right. See, we'll start with torque today. But before that, let us just revise cross product. So you all must have done cross product and dot product in your 11th standard. So just a basic of this revision of your cross product. While we are using cross product, we do multiplication of two vectors. So whenever you have two vectors, multiplication of two vectors, you use this cross product. And also, when a vector is multiplied with a vector, the resultant is also a vector. So result you get is also a vector. So if you have a vector B with you and you have a vector A with you, let's say the angle between the vector A and vector B is theta. So resultant means A cross B. This is given by magnitude of A, magnitude of B, sine of the angle between them means sine theta with a unit vector n cap. This n cap is mainly used to show the direction, in which direction or whatever is the direction. Because see, resultant is also a vector and you have two vectors. So whenever we write a vector, we don't only write its magnitude, we have to represent its direction as well. So that's why we use this n cap. And direction of A cross B is perpendicular to A as well as to B. Means whatever is this resultant, A cross B, this whole, it is the direction of it is perpendicular, or let me write direction of A cross B. This is perpendicular to both the vectors that you have, vector A and vector B. Also, one more thing, to find out if you have two vectors, like you have two unit vectors, I cap, j cap, you are multiplying I cross with j or j cross I or k cross j. So how do you do that? So the technique for this is simply write down all the three vectors, I, j, k, and start moving in one direction, like I cross j. So I cross j cap will give you k cap. So if you reverse this, means if you write j cap cross I cap, that will give you minus of k cap. So it's not like addition. In addition, you have 3 plus 1 will give you 4, 1 plus 3 will also give you 4. But in vectors, I cross j will give you k cap. But j cross I cap will not give you k cap. It will give you minus k cap. So direction will be opposite now in this case. Similarly, if you go from j cap to k cap, this is just a technique to remember. Most of you must be remembering this as well. If you go from j cap to k cap, if you move from, yes, anyone, if you move from j cap to k cap,
I cap.
I cap, you get I cap. And if you multiply k cross with j cap, then it will be negative, yes, minus of I cap. Similarly, the last one that is left, k cross I, if you move from k to I, k cap cross I cap will give you j cap. And I cap cross k cap will give you minus of j cap. So you have to remember which vector is coming first. That's why whenever we write torque, we never write F cross R. If it has written R cross F, then the formula for us also becomes R cross F only. Because of this only, the direction gets reversed. All right. So just note down the basics revision of vectors, then we'll begin with torque in your electric field. How many of you have your maths class on Monday on the same time that we have for our physics class? Khalid and Salman, I know. Anybody else? Salman and Khalid, you have your maths classes, no?
Yeah.
Yes.
Alright. Just write done in the chat box. I'll know that you have written it. Okay, okay, Salman. I thought it's in this only. Fine. So you and Khalid only have the same class.
Yeah, we are in a same class because we go to the
Okay.
same school, and
Okay.
there one sir is taking for us.
Okay, so by now most of you must have completed it. This is just your basic of your vectors which you have done. Vectors is utilized in torque whenever we are calculating torque. In the next part that we'll see electric flux and all those, there you need dot product. For just for now, I think revision of cross product is enough. Then we'll do discussion of dot product later on. So what is torque? Torque, as you must have studied in your rotational classes in 11th standard also, that these are rotational analog of force. Means whatever work is force doing in straight line in translatory motion, the same work is being done by torque in case of rotation. So any example where torque can be applied? Yes, no example of torque.
On the gear one, like pulling up a.
Pulling up. Yes, Khalid.
I don't remember the example. It's something related to pulling up of something.
It can be anything. Like if you take a rotation of fan is moving, so torque is applied at the axis where the ceiling fan that we have. So the blades of the fan are moving, and the axis to which the fan is hung, that is applying torque. So this can be an example of torque. If the fan starts moving, then we say force is there. But the fan is not moving. No, fan is stationary. Only the blades are rotating. So that we call as torque. This is the force. Where it is separated through a distance, means axis is separated through a distance where the motion is occurring. This can be taken. Okay, whenever there are two equal and opposite forces, they form a couple. We call it a couple. As if I tell you this is a rod, let's say a rod like this I have taken, this is a rod that has been taken. All right, so this rod must be having its distance, let's say small d is the distance, and I have applied a force in this direction, means in this manner, and other force is being applied in the downwards direction. So what is happening? One force is moving in one direction, other force is moving downwards. So this line, this imaginary line, if you extend this, these are known as lines of action. This is the line of action of this force, and this is the line of action of this force. So two equal forces are there. As you can see, F is the magnitude of both of these forces, and these are acting in opposite direction. One in J cap, other one is minus J cap. So this forms a couple. We call it a couple. And from your 11th standard, as I've told you also right now, R cross F. So what is R cross F? Calculate the torque, you take the perpendicular distance. Perpendicular distance means between this line of action. Line of action means the axis, the stationary axis that we say. So between this line of action and to the axis. Let's say this was the axis. Let's say this is just a random example. So D by 2 will become your R. Wherever is the stationary point, this is your axis, and the force is occurring. This distance will be taken as your R, perpendicular distance. Otherwise, if this is your axis, then this distance could have been taken. If this is the tip of the axis, then this could also have been taken. But no, we take the perpendicular distance. Even if you are not given the perpendicular distance, just you have to drop a perpendicular and consider the perpendicular distance only. So perpendicular distance between the lines of action multiplied with whatever is the magnitude of force. This is valid for a couple as well. This is valid for general formula of torque. But see, now we require dipole. We know what is a dipole and how to take out the relationship between torque and dipole. So yes, who is going to tell? Who remembers it? Huzaifa Ahmed, you tell me. What is the formula for dipole? Or at least, Huzaifa, you tell me, what do we call a dipole? What is meant by a dipole? Can I call plus 2 coulomb charge and minus 3 coulomb charge as dipole? No, Huzaifa, we cannot call minus 3 coulomb and plus 2 coulomb as a dipole. For a dipole, anyone else? What is meant by a dipole?
Ma'am, two equal and opposite charges when they're placed together.
Equal and opposite charges. No, Huzaifa, understand. If you have plus 2 coulomb with you, then you have to take minus 2 coulombs only. This forms your dipole. Not
I
2
thought you
coulomb.
said minus 2 and plus 2.
Okay, fine.
I'm sorry.
So you remember. All right. And what is the formula for dipole? Anyone?
P is equal to 2A times Q.
2A times Q. 2A is the separation between the charges and Q is the magnitude. Yes, right. So if we have to take out if the electric dipole is kept in uniform electric field. If this is called in electric field. Dipole in uniform electric field. So uniform electric field, as I have discussed with you, equidistant and parallel lines are represent your uniform electric field. If you have parallel lines with you which are placed at equidistant, then we say they form your dipole. So if I tell you, suppose I have a charge minus Q and I have a charge plus Q. So this is valid for the formation of a dipole. So let's say this is a dipole with the separation 2A or whatever is the separation between itself. So from the negative charge to the positive charge, if you remember, this is the direction for a dipole. So the direction of dipole will be in this manner from the negative to the positive. Now this charge is kept in the electric field. These lines, these yellow parallel lines represent the electric field. These are all the electric field lines. It means the dipole has been kept in electric field. Now plus Q charge is there. For positive charge, the direction of force is towards the electric field, along with the electric field. If the electric field is directed in right hand side, then the force will also be directed towards the right hand side. So this will be the direction of force, plus Q. That is plus QE. For a negative charge, the force direction of force is opposite to that of electric field. So if the electric field is directed towards the right hand side, then this force on this negative charge will be
Towards left.
towards the left hand side. Means in this manner, in the opposite direction. F force for the negative charge means minus Q. So F plus Q is acting in the right hand side, minus Q is acting in the in the opposite side, means in the left hand side. So if I take out the net force on the dipole, this will be the sum of the forces that are occurring, means plus QE 0, exactly, minus QE, these will get cancelled, it means 0. So if the net force is coming 0, both the forces are having the same magnitude is same, direction is opposite. So this is also making a couple. This can also be considered as an example of couple. So QE and minus QE, this makes a, all right. One more thing. Now let's just derive out what is the formula for torque whenever it is kept in electric field. So let me take a charge. Let's say this is minus Q charge, this is plus Q charge. Both of these are separated by the distance 2. Let's say this is the separation 2. So dipole has been placed in electric field. Electric field is existing. I'm not drawing all the electric field lines. Electric field is there. All the electric field lines are over here. So again, electric force will be occurring over here, plus QE, and electric force will be occurring for this charge, minus QE. These are forming a couple. But see, if we are required to calculate the torque, as I've told you, wherever force is occurring, that becomes your line of action. So if I extend them, this becomes my line of action. If you remember, just now I have told you, in case of a couple, means in this, if this force is acting in this direction, in the upwards direction, then this becomes your line of action. Similarly, if I just rotated the dipole, I've just kept the dipole in this manner. So this is the line of action for plus QE and this is the line of action for minus QE. But we require perpendicular distance for torque. So we'll just drop a perpendicular to the line of action. Let's say this point is some N. Let's name it as B. This is C. This is now a perpendicular. So a perpendicular has been drawn. Now torque will act on the dipole. Definitely, torque will act on the dipole. Torque will be acting on this dipole. And as I've told you, perpendicular distance between them multiplied by the magnitude of force. This is how you calculate torque. This is how the calculation of torque is done. So now see, if you consider this, torque will be, if you take the force is QE simply, but the perpendicular is BN and we don't know what is the perpendicular. So we have to just apply basic trigonometric values only. If I take sine theta in this, just a random angle I have taken and I am considering sine theta. Okay, sine theta, theta will be this. So look at this triangle ABN. What will be sine theta?
BN by AB.
BN by AB. This will be BN by AB. Sine theta will be BN by AB. Are we aware of AB? BN is unknown, definitely. Are we aware of AB?
Yes, teacher.
That is, yes, Atif?
2A.
2, correct. Yes. So Bn, which was unknown to us, is AB sine theta mainly. And Bn becomes AB is what? 2A
2A sin theta.
theta. Correct. Now let us put it in value of torque. This becomes 2A sine theta, and we have QE as well. Let us just shuffle it. Q, 2A together, because this is giving us something. Are you able to identify it?
Dipole.
Dipole. So now we have established a relation. This is your dipole moment. This is E sine theta. And when do we write any one vector as A, B sine theta? When we have taken their cross product. So torque basically means cross product of dipole and electric field. Is it clear?
Yes, ma'am.
All right. So just note it down. It's a iftar time over here, so I have to take a 10 minutes break. Then I'll continue. Till here is fine, Shravya?
Ma'am, like electric dipole in uniform electric.
This one?
Yes, ma'am. Just a minute.
All right.
Done, ma'am.
This part you're writing or you have written?
Writing, ma'am.
So all of you have completed?
Yes, teacher.
All right. Fine. Now see few important points that you should remember. Torque is what? Torque is the cross product of dipole and electric field. P cross E is basically PE sine theta. Sine theta means angle is considered between what? Angle is considered between the dipole and the electric field. So if the dipole is placed like this and electric field is like this, then whatever is the angle forming between P and E, that you have to take. That's how we take whenever we use cross products. All right. Now you should remember that torque, what does torque do or what is the function of torque? So torque will try to align the dipole in the direction of electric field. If the electric field is like this and dipole is kept slanting, then torque will try to move it and align the dipole in the direction of electric field. That is the function of torque. So if you have torque, just let me know when you all have written. Okay, all right, done, fine. So basically, torque will try to do what? Torque will try to rotate the dipole and align it with the direction of, align it in the direction of electric field. This basically means that this is giving us the direction of torque also. Like if I tell you what is the direction of torque, then the direction of torque is like this. This is the direction of torque only. No, torque is acting in the direction to make the dipole align in the direction of electric field. So dipole will rotate. The dipole that you have in the electric field, dipole will rotate by a very small angle, by smaller angle. Why will the dipole rotate? Dipole will rotate to align itself with the electric field. And who is doing this? Torque is allowing the dipole to rotate in the direction of electric field. So by smaller angle to align with E. E means electric field. This basically means if I represent you through electric field lines, if this is your electric field line, okay, all of these depict your electric field line, and the dipole has been placed like this. This is the dipole. This is the direction of the dipole that you have. This is the dipole. Now see, torque will try to rotate it clockwise. If this is the direction of your dipole, torque is trying to rotate it in the direction of electric field. This was your electric field, this was your torque. Torque is trying to rotate dipole. So this is what? Which direction is this? Clockwise or anti-clockwise? This is
Clockwise.
Clockwise. So torque will act in clockwise direction. That's how you will see the direction of torque. If you are given a system, just check in which direction is torque acting. How will you check in which direction is torque acting? You will see in which direction is it trying to align the dipole with electric field. Like if this was your question given, then you will see dipole is there, then torque will definitely try to act in clockwise direction, hence making dipole and electric field parallel, means having no angle, 0 degree. So this is the direction of torque now, clockwise. If we are given these are the electric field lines, but the direction of dipole is in this manner. So see, obviously, see, if this is the dipole, this is the electric field line, then torque won't act in this direction to make it align like this. This is the smaller, see what I've told you, by smaller angle. If the torque tries to move again in the clockwise direction like this to align with the electric field, this is the greater angle. It has to cover a long way. It prefers smaller angle, anti-clockwise in this manner. Here, this is how the torque will work to align it with the electric field. In either dipole was like this was the moment of dipole, it will act like this. So this direction that you are getting is anti-clockwise. Just note down these 2 points and I'm giving you a question, try it also. Till the time, just note down these 2 points. So electric field is given to you as 10 Newton per coulomb. One charge is minus 2 millicoulombs, other charge is 2 millicoulombs. Separation between these two charges is 3 millimeters. So by looking at minus 2 millicoulombs and plus 2 millicoulombs, you can easily say that this is forming a dipole. And the separation between them is 3 millimeter. What is this 60 degree? 60 degree is the angle between this dipole and the electric field. Now see how will torque function. We will see the direction later on, but without even specifying the direction, you can easily say the smaller angle is 60 degree. What will be the other angle? 300 degrees if it has to rotate, because the whole complete angle of a circle is 360 degrees. So it has to move either through 300 degrees or to 60 degrees. So which will it prefer? 60 degree or 300 degrees?
60 degrees.
60 degree, the smaller angle. So it means it has to align the dipole with the electric field. So 60 degree angle is required, means this angle will be considered. So direction of torque will be in this manner. So this is again clockwise. So direction of torque is clockwise. Now the magnitude of torque. Torque is what? It is P cross E or PE sine theta. Now we don't have P. E is provided, but P we have to find out. But we have sufficient data to find out P. P is what? Dipole moment, no? So P is formula of dipole is charge multiplied by the separation between the charges. Yes, Hania, what is Q?
2.
Only 2? Something else is also given. 2 coulombs is there? 2
2 into 10 raised to minus
minus
2.
3 millicoulomb. All right. So this is 2 into 10 to the power minus 3. Good, Hania. This is the charge that we have. And we can take any of the charges because the magnitude is same for both the charges. So 2A is there. Atif, you tell me, what is 2A over here?
3 into 10 raised to minus 3.
3 into 10 to the power minus 3. Correct. 3 into 10 to the power minus 3. So this gives us 6 into 10 to the power minus 6. This is the dipole that we have. Torque is what? Dipole multiplied by the electric field. So yes, Salman, tell me what is electric field?
Teacher, it will be 12, right? 12 into 10 raised to minus 6.
What?
It will be 12 into 10 raised to minus 6, right?
12 into 10 to the power minus 6 over here.
Yeah.
3 into 2 is 6.
2 is the charge, then 2A, right? 2 into 3.
2 is the charge. See, this is the charge. This is Q. This is 2A. See, Khalid, charge is 2 millicoulombs only. So charge is 2 into 10 to the power minus 3. 2A is equal to 3 into 10 to the power minus 3, no?
Oh, okay, teacher.
Okay, 2A is 3 millimeter. I think you got confused between this 2 and the 2 of the charge, no? All right.
Yeah.
Yes, Salman was telling us the electric field. Did he tell?
No, I didn't tell. My bad. 10.
Yes, correct. It will be 10. Yes, Memuna, what is sine theta?
Sine 60 degree.
Sine 60 degree. And what is the value of sine 60 degree?
Root 3 by 2.
Root 3 by 2. So this is 6 into 10 to the power minus 6 into 10 into root 3 by 2. So 2 will get multiplied. This will be 3. So torque will be 3 root 3 into 10 to the power minus 5 Newton. Meter will be the unit. And the direction of it is clockwise. So no, Shravya, the last part I think is not correct. Just check. Just look up your calculation.
30
Okay,
into
okay, okay. 3 into root 3 you have done. No, this is coming till here. It is
Yes.
fine. Good, good. Then your answer is right. Just note it down, all of you. I think you have written the question or not. Done?
Yes, ma'am.
All of you, Huzefa, Khalid, Sarah.
Yes, teacher.
Yes, ma'am.
All right, fine. Okay, just we have to discuss 3 special cases. What will happen if you remember these values, then your calculation becomes easier. First case is when the dipole is parallel to electric field. If the dipole is kept parallel to electric field. These are very small, very easy cases. So this is your electric field. Let's say the dipole is kept parallel in this manner. Now see, all of you write me in the chat box right now, what is the angle that I have to consider? No one will speak, just write me in the chat box. The sine theta that we take, what will be theta now? Okay, so Memuna and Atif are correct. Oh, which angle is this, Shavin? No. Yeah, now you are correct. 0 degrees. See, 180 degrees when both are kept parallel. parallel but in opposite direction. If P is here, E is here. This is 180 degree, no? The complete angle. When it forms a straight line. In this case, both are aligned together. You have to use this tip of both of them for your calculation. All right. So this becomes 0 degrees. Now, F net will always be 0 because dipole we have seen one is plus q, other one is minus q, that will get cancelled. Torque is PE sine 0, which is 0. So torque is also coming 0. This is the condition of stable equilibrium. Equilibrium is existing. It is a stable equilibrium. So this is a condition of stable equilibrium. So even theory questions can come from this part as well. In which case, in which angle is the equilibrium stable or unstable? Unstable we'll see. It's a case of stable equilibrium. Then the second case, if it is kept anti-parallel. When the dipole is anti-parallel to electric field, means these are your electric field lines. Dipole moment is now kept in this manner. Whenever I say it is kept in this manner, means the direction. Now you can identify where is the negative charge, where is the positive charge, because you know the direction. It is from the negative charge to the positive charge. So this must be the negative charge and this must be the positive charge. So this also you can identify. Now the angle. Now the angle, I think all of you know. This is the case of anti-parallel, which I was telling you. This is 180 degrees. Yes, Memona, right. This is 180 degrees. Both of them are anti-parallel to each other. Whenever two quantities are parallel to each other, angle is 0 degree. So theta will here be 0 degree, 180 degrees. See, F net will be equal to 0. Torque will be PE sine 180 degree. But see, in this case, again, it is coming out to be 0. But remember, what is happening? Now torque has to cover, if you displace the torque from its, not torque, I'm sorry, dipole. If you displace the dipole from its mean position in this manner, it will take a longer time to align itself. It won't be able to align itself. See, if this is the dipole that you have, and this, I have just disturbed it. That was its mean position. I have just disturbed it. So what will happen after disturbing? Because the angle is so large, torque will not be able to align it. So this is a case of equilibrium, but this becomes unstable equilibrium. See, you have two types of equilibriums with you. One is stable equilibrium, other is unstable equilibrium. In the case when I said that this was stable equilibrium, even if I displace it from its mean position, let's say I have displaced it in this manner, torque will be able to align it. It will reach its original position. Not even case of dipole. Even if you talk general, if you have a thing with you, anything, and you displace it from its mean position, and by the usage of any external force, any external torque or any external force, the body is able to regain to its mean position, then we say that equilibrium is stable. If we disturb the body and the body is not able to regain its original position, then we say that it is unstable kind of equilibrium. So in this case, this becomes your anti-parallel case, this becomes your unstable equilibrium. This is the condition of unstable equilibrium. So it is the condition of unstable equilibrium. The last case that you have, the last case is very easy. Case 3 says if dipole is perpendicular to electric field. So your electric field lines will run in this manner. These are your electric field lines. Dipole is kept perpendicular, means in this manner. So perpendicular, now you know angle is 90 degrees. So F net will definitely be 0, but now the torque won't be 0. PE sine 90. Sine 90 is not 0. Cos 90 is 0. Sine 90 is 1. So torque is equal to TE. So this is the maximum value. Maximum value of torque. So see, in this, numericals can come in which manner? Numericals aren't possible. Angle, you know, the result, you know, and maybe in this case, case 3, you get the value of dipole and electric field and you get the value of torque. But majorly theory questions are possible, in which case the dipole will have maximum value, in which case the condition of unstable equilibrium will persist. All right. So just copy these few points. So done. Yes, Atif, Hania written.
Teacher?
Yes, Mamana.
Teacher, maximum value in the sense it is maximum dipole.
No, maximum value in the sense as in if you change the value of angle, like what is the maximum value of sine theta possible? 1. 0 is the minimum value that we took for equilibrium position. Maximum value as in nothing angle is more possible than 1, because for sine theta we have sine theta is fixed. Now what is the maximum value of sine theta that you can have? For sine 90 as 1 only. So it means you are now free of angle. Now whatever is the value of the dipole and whatever is the value of electric field, you will get the torque itself. If you shift the angle means if you take not instead of sine 90, if you take sine 60 or sine 30, torque's value will be lesser than whatever is the value that you are getting through 90 degree. All right?
Okay, teacher.
Okay. In your class 11th, the last chapter that you must have done, your waves and SHM. In those SHM, we'll just do a very small revision of your SHM, because in some of the questions, this concept is utilized. So most of you must be remembering it because this was the last chapter only. So in SHM is simple harmonic motion. Basically, we will be dealing with angular SHM in this. Now, if I give you a random example that I have a string with me, and at the free end of the string is attached a bob. A bob is attached, and this is the mean position of it. Now I have shifted it to some angle, some very small angle. This pendulum, this is now a pendulum, the string attached to a bob. Now the pendulum, I have shifted it through very small angle, theta. Very small angle, I have shifted it using my force, external force. So using external force, I have shifted it. The restoring torque acts in case of angular SHM, which tries to shift. This is the restoring torque. This tries to shift the pendulum in the mean position that it was having. That is the function of the torque. Hello? Yes, this is not audible.
Now it's audible.
Somebody just said, is this audible now?
Now it's fine.
Okay. Now it's fine. See, if you have a pendulum with you and the pendulum, I have tilted it to some small angle. And the restoring force, the restoring torque is now shifting it back to its mean position. So the condition for any particle or any system to exhibit SHM or angular SHM, let's be very specific with angular SHM only. So first thing is that it should be oscillatory motion. It should show oscillations. Second case is that the restoring torque should act. Restoring force acts in case of normal linear SHM. In case of angular SHM, your restoring torque acts. So restoring torque acts, and the restoring torque formula becomes minus k theta. If you remember, for linear SHM, you have minus kx. This was your restoring force. This was the constant spring factor, which we say, and this is the displacement. Similarly, for angular, if you write the analogs in terms of rotation, torque, this is the constant that you use. Let me write whatever each term depicts. This is the torque, this is the restoring torque. This is the restoring torque. This constant is again, this is the constant, which we call as the spring factor. So for different system, it becomes different. For spring mass system, you have different. For pendulum, you have different systems. This has its own significance. And this is the angular displacement. Theta is the angular displacement. So any condition where restoring torque is directly proportional to theta means angular displacement and is directed towards the mean position. This negative sign shows that it is directed towards the mean position. Then we say the particle is executing angular SHM. So apart from this, if you have to calculate angular frequency, the formula becomes K divided by I. In case of rotation, you have I. In case of linear, when you were considering linear SHM, you had M. M was the mass. Now I is the moment of inertia. This is the moment of inertia. So for rotation, you have moment of inertia. Omega is the angular frequency. And if you know omega, you can easily calculate time period. This is 2 pi by omega, or omega is equal to 2 pi divided by t. So t is the time period. Revised? Your previous is clear? 11 standards SHM? Because we have some questions based on this only. Like you are given a question, if you are given a question, an electric dipole is placed in a uniform electric field. You have to show that its motion is SHM, means simple harmonic motion, and also calculate the time period. So I'll discuss it right now only. If you are given such question where SHM concept is used, do one thing, just draw all your electric field lines. These are your electric field lines. If this is the mean position of the dipole, this is the mean position of the dipole, then if I disturb its mean position, the way we have been doing it for pendulum, mean position to some slight angular shift means it has covered some angular displacement. Let's say this becomes theta. This is your dipole. Just relate it with a simple pendulum that you must have done. If the pendulum is this manner, you just shift it, apply an external force, then the restoring torque will try to align it back. Restoring force will try to align it in clockwise direction. Definitely, if I take this. Now see, if I talk about restoring torque. So torque is what? Minus PE sine theta in this case. Minus, I'm just trying to represent that it is trying to bring it back. Minus PE sine theta. Now see, using small angle approximation. Whenever you have sine theta and your angle is very small as in 15 degrees, less than 15 degrees, 10 degrees, 5 degrees, your angle is very small, then in such cases, sine theta is almost equal to theta. So instead of writing sine theta, or tan theta is also equal to theta, but here this can be written as theta. So now torque, that is minus PE sine theta, this becomes, because this is the restoring torque, that's why I have added this negative sign. This becomes minus PE theta only. If I compare it with minus K theta, what is the value of K now? Yes, compare both these two equations.
PE.
Instead of K, what do you have in this equation?
PE.
EE.
PE. Yes, Atif, Khalid, both of them have answered only. Just compare these two equations, no? Torque is this. This is the restoring torque that you have. This is the restoring torque. And in our main equation that we have discussed just now for angular SHM, restoring torque is required. Negative sign to depict it is directed towards mean position and it is trying to align it. All right. Theta is the angular displacement. This is the angular displacement. So what is left? Here K is left and here PE is left. Means whatever is the value of K is the value of PE. So K is equal to PE. Now you have your constant with you. And in this equation also torque is directly proportional to theta. That's why we are saying torque is equal to PE theta. Means this is a condition of SHM. This has been specified. This is following. This was the condition of SHM. This was your condition of SHM. So this shows that the system exhibits SHM. It has also asked us to calculate the time period. So for calculation of time period, we require omega, that is the angular frequency. So see, angular frequency is equal to what? Angular frequency is equal to K divided by I, moment of inertia. K is PE, so PE divided by I is omega. Time period is 2 pi divided by omega. You have the value of omega with you. So time period becomes 2 pi divided by under root PE. And your root I goes up. Means T will be equal to 2 pi under root I by PE. You've just divided 2 pi by under root PE by I. Because why you have divided? Because omega is this. So this is the value of your time period. If it's a numerical kind of question, then they will be providing you values of charges, their separation, electric field, as well as the moment of inertia for the dipole. All right, so this is how you have to tackle if your SHM is included in your torque questions. Is this clear to all of you? Shravya, Salman, Khalid, Memuna?
Yes, teacher.
All right, just note it down. Yes, completed?
Yes.
All of you?
Yes, teacher.
Yes.
All right. Now see one last topic that is included in your torque. This torque is over. See, we were considering electric field that was uniform. What happens, or if the question says discuss the motion of dipole in non-uniform electric field. If non-uniform electric field has been specified. So now electric field lines won't be equidistant to each other. They will be at some different distances because these are not now uniform. So let us say the dipole is kept. The dipole is this is your dipole which is kept. Now electric fields will be different. This is E1, this is E2. So if I say this was the charge plus Q and this was the charge minus Q, this is the dipole that we have. Now see, if this is your dipole that we have, force over here, electric force over here, this will be Q E1, not QE only. It will be QE1 plus QE1. Here the force which will be directed in the opposite direction, this will be minus QE2. So if we calculate the net force on the dipole, this will be, F net will be QE1 minus QE2. Will it still be 0?
No,
It
ma'am.
won't be 0 now. F will have some value. It won't be equal to 0. So if your force is not equal to 0, this means there will be some translation motion. Means the dipole will be moving also because force is there. So here it will have translational motion. Also, if we talk about the torque will be equal to PE sine theta. So torque is anyways not having any value of 0. We had seen torque will have different value. Torque will only be 0 in case of 180 degree and 0 degrees that we have seen. So torque is not equal to 0, means torque also has some value. So this means it will have rotational motion, that we know it. That's why the torque was trying to align the dipole in the direction of electric field. So it will have rotational motion as well. So your final motion, this will be a combination of translational motion as well as rotational motion. Clear?
Yes.
Translational as well as rotational motion. Translational as rotational motion, as well as your rotational motion. Fine, just note it down.
Done, ma'am.
All of you?
Yes.
All right, fine. So this completes your talk. So we'll continue your electric flux and revise cross product and dot product. Cross product we have discussed, dot product we'll start. All right, okay, thank you.